The Power of Electricity. A physics project by Juan, Emerson, and David.
Oh man, it's so hard to see in the dark. If there was only a portable light source, but that's impossible. Are you a wizard?
No, it's science. It's actually called electricity. See, electricity powers the big and the small, factories, and even this computer right here. However, before I get into how useful it is, we first have to explain what it is. What is electricity? Electricity is the transfer of electrons, which are little tiny negatively charged particles that exist inside atoms. But in materials like copper and gold, some of these electrons are able to move freely. Now, when a lot of electrons move in the same direction, like going into your phone or your TV or any electrical device, that is when an electric current is made. The unit for current is amps, which might sound familiar, but think of it like this. The wire is a highway, and the electrons are the cars. That means that the current is the traffic flow. So, the more cars on the highway, the more current that the particular wire is experiencing. Then there's voltage, which is the amount of electrical potential energy per unit charge between 2 points in a circuit. Yes, I know it sounds really complicated, but it's really not. Think of it like this. Voltage is the push that causes electrons to move through a wire. So that's also measured in V, volts. And another way to think about it is water flowing through pipes. So think of it as the voltage is the water pressure, the current is the amount of water flowing, and the wire is the pipe. So the more pressure there is, the more of a drop there will be between one section and another one, meaning that there's more voltage, so electrical potential difference. Then there's power, which is the rate at which electrical energy is transferred and or used. This is what allows devices like your phone, lights, computers, and entire cities to function. Without electrical power, most modern technology would simply not work. A simple way to understand it is, again, imagine water flowing through a pipe, where the voltage is the water pressure, the current is the water flow, and this time the power is the amount of work the water can do, like the water turning a wheel, pushing a gate, and etc. The greater the flow and the pressure, the more powerful the system becomes. Okay, now, there are two different types of electricity, AC and DC. DC stands for direct current, which means that electrons flow only in one direction through a circuit in a constant current. Batteries produce DC because of chemical reactions that occur in the battery to create a constant voltage. Some examples of DC devices are flashlights, phones, laptops, electric cars, and more. Now, some characteristics of DC are that it's a constant voltage, it's a constant flow of electrons, so it'll always be going from point A to B, and it won't go from B to A. And now, finally, is that these are the best for electronics and energy storage, because that's why your phone charges. If the current just goes from A to B, let's say that A is the wire or the outlet, and B is the phone, if it only goes from A to B, that means that your phone is going to continue charging. That means, well, better for you, it means that no current is going to go back into the wall. So instead of having a circuit, it's just going to be a direct flow, and you're just going to charge up your battery. AC stands for alternating current, which means that electrons repeatedly reverse direction. So in simple terms, they go back and forth. For example, the US AC changes direction 60 times per second, hence why it's 60 hertz. AC is made in big power plants by generators when a magnet rotates near a coil of wire, and the constant changing of magnetic field induces a change in voltage through electromagnetic induction, which is the process of generating an electric current in a conductor by varying the magnetic field around it. Since the magnetic field keeps changing direction during its rotation, the current also changes direction, hence why it goes back and forth. See, now AC is really important because it can be transported very long distances all the way to your house through transformers, which increase voltage to send it to your house, school, neighborhood, or whatever building there is. And then it is stepped down again by other transformers, so you can actually use it at your house and at your home, school, wherever you're at. Now, some examples are wall outlets, microwaves, fridges, and lastly, your TV.
Okay, so now that we know how electricity works, Now we're diving into the funnest part. Can you guess it? Yes, it's everyone's favorite subject, math. Okay. It might not be everyone's favorite subject. No need to boo me, but it's gonna make solving for electricity so much easier. First and foremost, we have Ohm's law. Ohm's law defines the fundamental linear relationship between voltage, current, and resistance in an electrical circuit. What is a circuit? A circuit is a closed path or loop that allows electricity to flow from a source through components and back to that source, which allows electrons to flow continuously, allowing energy to flow through components. In Ohm's law, there are three terms we're going to be defining. First, voltage, which defines the electric potential between 2 points, which is measured in volts. Second, we have current. Current is the rate at which charge flows past a point in a complete circuit, which is measured in amperemeters. And finally, we have resistors. A resistor is a passive two-terminal component that limits or regulates the flow of electric current through a circuit. This is measured in ohms. Allows us to use the next model, which is my personal favorite, the Viper table. This allows us to solve for current, volts, and the resistance of a current circuit with the given bonus of solving power. To use the Viper table, I'm going to be talking about circuits again. This is two types of circuits, parallel and series. In a parallel circuit, voltage of all the nodes will be the same because it ends at these two same points, and as I said before, voltage is the potential difference between 2 points of a circuit. Another circuit is a series circuit, which this circuit will have the same current going through all the resistors. Once you find one current for a resistor in a series, you can find every other current. And once you find one voltage of a branch of a parallel circuit, you can find every other. Okay, I think that's it. Oh, but we have one more circuit to talk about. This circuit is called the complex circuit. I know the name might seem scary, but it's a combination of the two circuits, the parallel and the series. Once you know both of their roles, you should be able to find the current, the resistors, and the voltage using the Viper table. Just make sure you label your data right. And to test understanding, we're going to be solving a simple complex circuit problem. This circuit will kind of represent the wires of your house for a light bulb. Okay, the circuit that you're going to be solving is the circuit that you see right here. Everything that you will need will be up on the screen. The equations and the stuff to remember. Pause the video. And once you're done, unpause it and I'll show you the answer. Good luck. Okay, have you solved the circuit? Compare your answer with mine. See if you got it right. If you got it right, congrats. If you didn't, see what you got wrong. It takes time to take this talkbook down, but once you get the topic, it should be easy in no time. This is the end of the math section. Now, we're going to be talking about the real life examples of electricity and why it matters. Take it on, my fellow scientists.
One everyday example of electricity's power at work is in an oven. An oven is often one of the two things that takes 240 volts of AC current to power it. It feeds the electricity through wires, often thick ones, and the resistance of those wires creates heat. The energy from the electricity can't get through the wire easily, so its energy is lost as heat instead. The high voltage allows for lots of power to be exerted by the wires in the P equals IV equation, and this heat goes into the oven chamber to heat up your yummy favorites. Another everyday example of electrical circuits at work is through the lights in your room or your house. Lights are often wired in parallel, allowing for the same voltage to be across each light. This means the brightness of your light bulb, assuming they are the same light bulbs, will be consistent. When you flip on the switch, the electrons travel rapidly through all the light bulbs. Inside the light bulbs, often LED bulbs, the electrons pass through a semiconductor, causing electrons to release energy as photons, or light. Again, this is one of the advantages of parallel circuits, allowing for consistent voltage across all the light bulbs. Thank you so much for listening to our video, and have a great night.